This one is the second question of beams. It says a beam which is drawn to a scale of 1:100 and an outline scale of 1 mm is 10 newtons. We are required graphically and analytically find the magnitude of the reactions RL and RR, draw the funicular polygon, find maximum bending moment, position of resultant relative to RR, and also free and sketch of a typical beam to carry the loads. And the last one, you have to draw the shear force diagram and label zero shear. Right, so as you can see, I have already done the Bose notation. Your RL to 250, that's your first space, so you label this as I. And next one, (250 to 400) is your space B. 400 to 150 is your space C, and 150 to RR is your space D. RR to RL will be your space E. After that, you're going to complete the load line, and to do that, you have to know how to use the scale. The scale says 1 mm is 10 newtons. This means all the distance, all the forces here, I have to divide it by 10. So I to B is 250, 250 divided by 10 is 25, B to C 400 divided by 10, 40, C to D 150 divided by 10 is 15. So I'll measure I to B, that's 25, B to C 40, and C to D 15. Then I'll join all the points to O. That diagram will be a polar diagram. And also draw the arrows here. Right, so once you have completed your polar diagram, your next step, you're going to take all the points straight down, and then you're going to transfer A0, B0, C0 and D0 on the relative spaces. We're going to start our diagram from here because we'll be drawing also the shear force diagram. So this is what we can do actually to know where we can start from. Right, so D is the last point there. This means your shear force diagram is going to finish there. So when I draw my funicular polygon, I can draw anywhere at that place. This is the space that I have for the funicular polygon. You can also start there, but your diagram is going to be complicated. Why did I put my A here? Because according to the Bose notation, my A is from RL to 250 newtons, and that falls outside, so my I naught will be outside. That is B0. If you look at B0 from 250 to 400, So from here to there is B0. Next we can take C0. And then you can take D0. But as you can see, your C0 is between these two forces and your D0 is between these two forces. Now your E is from RR to RL. So I'm going to join from this point till this point. I'm not joining to join it here because your E is from this line to that line only. You can label this as your funicular polygon. Right, and then you're going to transfer your closure. You're going to take parallel to this group, yeah, and transfer your closure there. This is your point E. That's your E0 and that's your closure. Now your RL is from E to A, RR is from D to E. So you're going to measure A to E, measure the distance. Now your scale is 1 mm is 10 newtons. This means if I measure this much, I have to multiply by 10, then I'll get the answer in newtons. Likewise, RR, D to E, from here to there, I measure that much and multiply by 10 and get the answer here. So when I measure that, D to E, my answer comes to 270 newtons. A to E, so when I measure A to E, my answer comes to 530 newtons. So when you add 250 plus 400 plus 150, you are going to get a total of 800. So 530 plus 270 will also give you a total of 800. You can also write the answers here. Right, so funicular polygon already done. Now to get the maximum bending moment. So for that we have to first find the bending moment scale. So here's my bending moment calculation. First of all, you have to find the bending moment scale. That will be PT, polar distance, which is the perpendicular distance from here to there, and that comes to 80 mm. Then your space diagram scale, which is 1:100. So we have to have in meters. It will be 100 divided by 1000. And then your load line scale, which is 1:10. So we'll take 10 there, which means after the calculation, we are getting 1 mm is equal to 80 Newton meter. This means every 1 mm that I measure from the bending moment will be equal to 80 Newton meter of bending. So if I look at my bending moment of irregular polygon diagram, at 250 I have 0 there because I can't measure any distance there. At 400 I have 20 mm from this point to that point. That's how you measure. At 20. At 150 I'm getting 15 mm. Measure from here to there. So maximum is this one. So 20 multiplied by scale and you're getting a bending moment of 1600 Newton meters. So that's what I can do, write it here. Now locate the position of the result relative to RR. You're going to extend the first force. You extend the last one, D0. And you're going to take this point straight up. Right, so when you take that point up, you'll extend your I0, D0, take this point straight up, and you're getting an intersection, you're getting the result in here. So you can label it as RES with 800 newtons as a force. Now it says it has to be relative to RR. From there to there, when I measure, I get 84. So 84 times 100, because my space diagram scale is 1:100. I get 8400 mm or 8.4 meters. A freehand sketch, you can simply draw an I-beam there, freehand. Draw a shear force diagram and label 0 shear. So to get the shear force diagram, first of all, you need to take all those forces this side, and then from there we'll outline. Right, I have taken all my forces this side. Now I'm going to outline. The first one is A, and my space A is outside. So if I make this line dark, or even if I leave it outside, it won't make any difference. Next one is B. B is from this point to that point. Oh, the point is here. Right? From here to there, that's B, so I'll make that much dark. Then from this point to that point is C. So if I look at my C, which is here, then from this point to that point is D, which is the last one. Now there's one more line in the middle, E. E is coming from this corner to that corner. We'll make all of that dark. Right, so when I make it dark, this will come like this. This will go and join it to C. C will be joined to D. Then D will be joined back to E. So this is value 0 shear is. This one is positive shear, and this one is negative shear.